Welcome, and my name is Elton, a co-founder to Micro Drainage Concept, launched in 2016. This is a trademark is focused to train people and get more understanding of how soil structure performs underneath the surface. By the farmer, for the farmer. In other words, we want farmers to be included in our micro drainage concepts, meaning providing test plots based on depth, spacings, and extracting yield data accordingly to maximize our performance. Here is a 3-point towel plow with a 2-inch boot up through to 6-inch by just changing the boot. In the back we have a towel cutter, crusher, and a feeder. It has a pressure reducing valve that gives us constant uniform pressure even if you're driving different speeds. That can be adjusted accordingly. At the end of the lateral, it cuts it off and crushes it on a half moon about 16 inches of length and feeds through the boot with the half moon upright, and the dirt falls on top and seals it off. No need for end caps. Then the front mount towel reel on the front of the tractor is mounted by 2 mounting points on the front and about 2 feet farther back to get more support stability. It also swings to the side and tips forward. That way you can drive forward and load your towel up. It also has a motor on platform to turn forward. That way it unravels the correct speed, either auto or manual on a dial. Since you're using GPS for grade control, the front mount towel reel and towel cutter and a feeder, it can be run by one-man operation focused on efficiency. Look closely. This is a 90-acre field installed on 20-foot spacings, and the laterals are not straight due to more of a contour style of drainage. We want to cut that water flow perpendicular, so we try to keep our laterals under 2% grade at all times. Due to GPS grade control, we can wrap around our hills and still get an adequate lateral length. And also, we can maintain an optimum uniform depth to get and quicker shallow drainage. Also, the spaces we try to keep at 20 foot or less to maintain our quicker drainage function. The benefits to our concept that we have more uniform yield, soil temperature increases quicker, less compaction, quicker in fields, and utilize maximum performance of the plants. Here is our agenda, what we are going to talk about. First, we are going to give a short history of the studies that were done before our time. Second is how our water table function in the soil. Third, depth and spacings of how critical it is to get top performance. Fourth, perpendicular drainage of how important it is to intercept the water flow to get proper drainage. Fifth is a higher velocity in smaller drainage pipes. This test was done in Ontario, Canada, involved Purcell brothers done by University of Guelph to prove if they function the same. Here it goes. Small diameter plastic tubing, 50 mm is obviously 2-inch or less in diameter, is commonly used as a drainage lateral in Europe, whereas North American, the common lateral diameter is 100 mm, 4 inches. Adapting this European practice in Ontario has the potential to reduce the cost of drainage material and installation. The literature search revealed that the capacity of a 100 mm diameter tile greatly exceeds the flow requirements of typical drainage lateral. The search identified that the main reasons for the recommendation of larger diameter tubing involve concerns related to increasing internal siltation and reduced performance due to poor installation and drainage design practices. A field survey was completed to investigate the condition of small diameter drainage pipes installed between 1984 and 1987 on 5 trial sites on farms in Ontario. All excavated tiles were found to be capable of performing a drainage function. The limited siltation found in the tiles appeared to be caused by localized grade control problems. A laboratory experiment was conducted to compare the flow velocities and corresponding siltation conditions for small and conventional sized tiles. Flow rates equivalent to expect actual field flow rates were used. In most circumstances, the flow velocity in small diameter tile exceeded the flow velocity estimated to occur in the larger tile. The only exceptions occurred when the flow rate approached the maximum non-pressure flow capacity of the smaller tile. In this study shows that between the plots were all the same spacings, depth, and had a flow meter on end to calculate the volume. Regardless of the tile sizes, the volume was the same, and they dug up laterals to find that smaller pipe had less siltation problems due to higher velocity. This chart shows what most commonly laterals used in different countries. Here it goes. Turkey, well, it's 50 millimeters is 2 inch and 100 millimeters is 4 inch. So Turkey got 50 to 100, Egypt got 80, Netherlands got 60, United Kingdom got 50, Belgium 50 outside diameter, Spain 50, United States 100, Ontario 100, New Zealand 62.5, and the last one is 60. A horizon is the topmost mineral horizon, often referred to as topsoil. This layer generally contains enough particles to decompose humidified organic matter to give the soil a color darker than that of the lower horizon. This layer is known as the zone in which the most biological activity occurs. Also, it has a lot higher percolation rate due to the pores are larger by the biological activity. B horizon is commonly referred to as the subsoil. In humid regions, B horizons are the layers of maximum accumulation of minerals such as silicate, clays, iron, and organic material, wherein the material gradually wash in from the overlaying horizons, where all the roots and worms and has fair amount lively soil activity and a higher percolation rate. C horizon is below the zones of greatest biological activity, and it has not been sufficiently altered by soil genius to qualify as a B horizon. While loose enough to be dug with a shovel, the A and B layers usually originate from the C horizon. It also contains layers of tight clay soils, which is used to create ponds or to seal off areas to divert water flows. Right placement. Our thought process is, why do we want our laterals in the C horizon, where percolation is very poor, but try to keep approximately at 24 inches of uniform depth? That way we can have a quicker drainage function. Infiltration is the process by which water on the ground surface enters the soil. Infiltration rate in soil science is measured of rate at which soil is able to absorb rainfall irrigation. It is measured in inches per hour or millimeters per hour. The rate decreases as the soil becomes saturated. If the precipitation rate exceeds the infiltration rate, runoff will occur. Unsaturated zone is part of the earth between the land surface and the top of the water zone. The position at which the groundwater, the water in the soil pores, is at atmospheric pressure. Hence, the unsaturated zone extends from the top of the ground surface to the water table. Capillary fringe is surface layer in which groundwater seeps up from water table by capillary action to fill pores. Pores at the base of the capillary fringe are filled with water due to tension saturation. The saturated portion of the capillary fringe is less than the total capillary rise because of the presence of a mix in pore size. If pore size is small and relatively uniform, it is possible that soils can be completely saturated with water for several feet above water table. Capillary action supports a shallow zone above the saturated base, within which water content decreases with distance above the water table. Saturated zone is the area of an aquifer below the water table in which relatively are pores and fractures are saturated with water. Saturation is when the soil is completely full with water and it starts to run off the top down to the creeks. Fill capacity is when the soil quits percolating down to the drainage pipe. Soil percolation works similar to a sponge. Drop it in a body of water, then remove and wait till it quits dripping, but it still has a fair amount of water. What is left is used for the plants. Wilting point is when there is not enough water for the plant. It starts to wilt up. Let's look at the chart to the left. Obviously, different soil types vary, but you see 100 grams of dirt. When it's completely saturated, it has 40 milliliters of water. At fill capacity, the same amount of dirt, it shows 20 milliliters of water. At wilting point, we have only 10 milliliters left. The questions come up many times as can we overdrain soil by too close of spacings? No, the reason you can is soil holds a fair amount of water for the plants and it's not drained well. And if it's not drained well, there's not enough oxygen for the plant. That is the reason for our shallow drainage to retain water for in the dry year. Here is a chart how soil percolation functions, time-lapse photographs of infiltration along a vertical soil section. The time indicated are in minutes after the application of the 0.4 centimeters equivalent 0.16 inch pressure head and represents periods A and B during infiltration, C at the end of infiltration, and D following the redistribution. Arrow indicates the location of early dye solution breakthrough in worm burrows. Note the T1 disc extended over the vertical soil face at the top of the photographs. If you see the time frame between each photo, A is 6 minutes at 10 centimeters 4 inches, B is at 15 minutes at 30 centimeters equivalent 12 inches, C is at 29 minutes 40 centimeters 16 inches of depth, D is 51 minutes at 45 centimeters 18 inches. The first three photos are percolating. As you can see, they're glossy, and the last photo soil is absorbing the water. As you notice how fast it percolates in the first two photos. It took 15 minutes to percolate 30 centimeters 12 inches, and the last 14 minutes it took 10 centimeters 4 inches. Here's another reason why for shallow drainage, due to it has higher percolation rate in the first 12 inches. Possibility of more biological soil activity has a higher pore space and comes down to your organic matter has a very important part on your drainage function. Here it shows between narrow versus wide drainage tile spacings at crop performance. As you can see where the groundwater levels are between time frame. If you notice, wider spacings has more uneven corn due it only drain X amount per side. If we can get the correct spacings and depth, we get more uniform corn yield. Depth and spacings. Let's say on the left we have 40-foot spacings and 3 foot of depth. On right we got 20 foot of spacings and 2 foot of depth. Water table. If you notice, the water bubble between tile lines is larger than the other. And also water table is closer to the top. Because of narrow spacings, the water bubble is smaller. It also intercepts the tile quicker due it only has 10 feet to go from center of bubble to it intercepts the tile rather than 20 feet till it intercepts on 40-foot spacings, and still maintain our optimum root depths. This way we retain our water table but not draining that deep. Benefits are we get to field capacity quicker, have it in reserve in a dry year, quicker increase in soil temperatures, less compaction, more oxygen, and many more benefits. This chart shows residual water per running foot, meaning when soil is completely saturated to field capacity. Based on spacings and depth at field capacity above tile line, it starts at 2 foot of depth, 20-foot spacings. Every dot increases 3 inches of depth per 5-foot spacings interval. So if you look at the first dot, 2 foot of depth, 20-foot spacings has 120 gallons of residual water. 3 foot of depth, 40-foot spacings has 359 gallons to percolate in tile. This chart shows time to drain residual water per running foot of tile based on depth and spacings at field capacity using 3/8 coefficient. It starts at 2 foot of depth and 20-foot spacings. Every dot is increased 3 inches of depth per 5-foot spacing interval. So if you look at the first dot, 2 foot of depth, 20-foot spacings, it takes 26 days to drain the residual water. 3 foot of depth, 40-foot spacings, it takes 38 days to percolate. This is only calculated vertical, not horizontal. The wider your spacing are, the longer it will take to funnel the residual water to tile. It is no easy way to calculate horizontal time. It takes about 50% more time to drain between 20 versus 40-foot spacings. Sports fields. There is science behind sports fields of their shallow depth of 1 foot and narrow spacings of 5 foot, due for a quicker drainage function to keep grass at maximum potential at all times. Retrofit for agriculture. So why can this be applied to farm ground? We know the depth is a limiting factor, but that doesn't mean we could maintain a 24-inch uniform depth if properly designed. For spacing, it's also a limiting factor due of cost. They also use 2-inch drainage pipe because their capacity exceeded their percolation rate due to closer spacings. It also is easy to install and less cost per foot. We also know to backfill with sand is costly, but that is why to bring our laterals closer to surface. Surface flow passes is the flow of water that occurs when excess storm water and meltwater. This might occur because soil is saturated to full capacity, because rain arises more quickly than soil can absorb it. Surface runoff is a major component of water cycle. It also primarily agent in soil erosion by water. Subsurface flow is a flow of water beneath Earth's surface as part of the water cycle. In the water cycle, when precipitation falls on the Earth's land, flow within the soil body may take place under unsaturated conditions. But faster subsurface flow is associated with localized soil saturation. Water flows least resistant, right? Now look at your chart. We all know water goes downhill. If you see the micro flow path starts forming, then it starts to develop a macro flow path, which means an waterway. Then from there it goes into the creek. The surface flow path is similar to subsurface. Describing groundwater flow using equipotential lines. Looking at the left picture, it is evident that groundwater flow is in the direction of the blue arrows, which follow the steepest grade at the surface of the water table. These arrows are at right angles to groundwater contour lines. The construction of contour line is not limited just to depicting changes in grade at the surface of the earth. Contour line can also be drawn to to depict the elevation grade at the water table, just as water flowing down a slope during a rainstorm is at the right angle of the construction contour line in the topography map. At any given point, the steepest slope is always at the right angle to the unique contour line could be constructed to intersect that point. The number written on contour line indicate the elevation of the lines. The elevation of contour lines can be determined using the contour interval. You can calculate the elevation of any contour line. Perpendicular drainage is to cut off water flow with your towel lines, which represents equipotential line to create a Quigger drainage function. On right, it shows a chart of a motor magnetic field which functions the same in drainage flow passes. Waterways. On left, we have a wide waterway. As you see, there is a tremendous amount of settlement problems with slower flow rates. On right, we have a narrow waterway. Having a higher velocity creates erosion problems. According to study, same in smaller pipe, slope had a large effect on velocities in the small and large diameter tiles. Flow velocities were higher in the silted tiles versus the unsilted tile of equal diameter. At high tile slopes, the flow velocity in small tile was always higher than the flow velocity in the larger diameter tile. At low tile slopes and lower flow rates, the small diameter tile had higher average flow velocity. At low tile slopes and high flow rates, the larger tubing had higher flow velocity. For the flow rates used, the differences in velocities between the tile diameters were relatively small. The laboratory tests showed that for most of the flow conditions, tile slopes and silt levels tested, the flow velocities within the small tiles exceeded the flow velocities of the larger tiles. Since velocity is a major criterion affecting silt movement in the tile and consequences selection of the tile diameter, this information of interest since it is different from the previous thinking of basis of which larger diameter tiles were specified because they were believed to have higher flow velocities. Thanks. Any questions? So who's interested in participating providing raw GPS data of tile lines for creating maps by color codes? Let's say green is 24 inches of depth, red is 36 inches of depth, and different spacings another set of colors. Then we also need raw yield data of the same field by putting yield layer on top of tile map. Then we can analyze of how much yield increase we have on depth and spacings by defining if it pays or not. So please contact us for further assistance at 419-908-5696. Thanks for watching.